we've been hearing a lot the last couple of days about COMO catalysts, and the next contribution by the Al2O3 Research Laboratory to bring a new element, iridium, into the picture. The paper is by Herbst and Rosen, and Dr. Herbst will present the paper.
Introduction. In my first year at Al2O3, I was a postdoc student and carrying out an investigation on heterobimetallic cluster compounds, and this investigation gave rise to a current project on iridium-promoted molybdenum catalysts for HDS and HDN. I would like to summarize briefly the results of this cluster project before I discuss more in detail the results of this project on iridium-promoted molybdenum catalysts. In molybdenum chemistry, there is this molybdenum 3s4 cluster core, which can be isolated from aqueous phase with 9 aqua water ligands around it. This cluster is usually referred as a geometrically incomplete Cobain-like cluster, and this is because it forms a kind of a cube in which one vertex is missing. This missing vertex can be filled by a reaction with metal compounds, and in aqueous phase about 20 different heterobimetallic systems have been isolated. In the case of cobalt and nickel, these heterobimetallic systems were taken as model compounds for the active sites of cobalt moly and nickel moly hydrotreating clusters. But we thought in order to study the interaction of such a cluster with organosulfur and organonitrogen molecules, it would be necessary to do this in organic media where these molecules are soluble. So we exchanged water ligands at this molybdenum cluster for methyl cyclopentadiene ligands. Then this cluster material is soluble in organic media, and we could react it with metal alkene compounds. In the case of nickel, we got a reaction with nickel COD and observed indeed the incorporation of a nickel atom in this molybdenum cluster. After that, we could coordinate this series of organosulfur and organonitrogen molecules to the free site at the nickel cluster. We could isolate all these compounds and could crystallize 2 of these clusters with the dithiene and with a bipyridine. And I will briefly show you the crystal structure of these 2 clusters. We have here the dithiene ligand coordinated via the S atom to the nickel site, and here the bipyridine coordinated to the nickel site. But we could not only react this cluster, molybdenum cluster, with nickel and cobalt complexes, but also with noble metal alkene complexes. And we got indeed the insertion of all 6 platinum metals into the molybdenum cluster core. In case of ruthenium and osmium, 2 carbonyl ligands were at the heterometal. In case of rhodium, iridium, palladium, and platinum, there was a triphenyl phosphane ligand on the heterometal, and for rhodium and iridium additionally a fluoroligand. most of these clusters were unprecedented in the literature, and we were of course very excited to see if these clusters show any activity in a hydrotreating experiment. So what we did, we impregnated alumina with solutions of these clusters and put it in a hydrotreating reactor with a model feed. This model feed is containing dibenzothiophenone, indole, and naphthalene. And the catalysts had a molybdenum load of about 8% and a noble metal load between 3% and 5%, which is depending of the molecular weight. The results for the activities which you see here are referenced to a pure molybdenum sulfide catalyst on alumina. You can see the highest activity was obtained for these group 9 metals, rhodium and iridium, especially in this is especially true for iridium. Ruthenium could not compete with the rhodium and iridium, which is a bit surprising since ruthenium is also known as a very good hydrotreating catalyst. But these enhanced activities for iridium were interesting enough for us to say we want to investigate this system further and see if we can learn something from this system for making better catalysts. The first question which we tried to answer was, does the geometry of the molybdenum iridium cluster give any benefit for the activity in comparison to a conventionally prepared two-step impregnated catalyst? So we impregnated a molybdenum catalyst with a solution of this iridium compound here, this cyclooctene chloroiridium dimer, and made a hydrotreating experiment in the same way as we did for the cluster, and we observed even a higher activity for this two-step impregnated catalyst. The reason for that might be that we have a lot of carbon ligands on the molybdenum and also on the iridium, which will not fully decompose and cause deactivation phenomena in comparison to this two-step impregnated system. But so we decided to go on with more experiments just with this conventionally prepared two-step impregnated systems. This approach had, of course, the advantage that we could vary the iridium-molybdenum ratio and investigate the dependence of the activity from the iridium load and from the molybdenum load. You can see here a plot of the dependence of the activity from the molybdenum load with a constant iridium load of about 3%. The molybdenum load is between 5% and about 20%. Only for these very low loads of about 5%, one might see a drop in activity. But for the rest of this series, between 7 and 20%, the activity is rather constant. A very different picture is obtained for iridium. Here we have a constant molybdenum load, and the iridium load is varying between 1.8% and 4.8%, and we observe almost a doubling of catalyst activity with increasing iridium load. Another question which was interesting to us was the influence of the structure of the iridium source on the catalyst activity. So we prepared a series of molybdenum iridium catalysts from these 3 iridium sources. We have on the left tris-acetyl-acetonato iridium. This complex is very soluble in most organic media, but it is insoluble in water, and it is rather stable towards higher temperatures. It is reported to decompose at 290 degrees C. In the middle we have hexamine iridium trichloride, which is very easily soluble in water and not very stable against high temperature. And on the right side we have tetrairidium dodecarbonyl. This compound has the advantage that only volatile carbon monoxide is formed at higher temperatures, so this compound might liberate very pure iridium. We prepared a series of clusters, both in the combination molybdenum iridium, but also the pure iridium ones. This entry 1 is the original molybdenum catalyst, which we used with about 15.2% molybdenum on it. The iridium load was analyzed to lie between about 2.6% and 3.50%. And for comparative reasons, we also prepared these pure iridium catalysts. The BET surface of these catalysts shows a very narrow distribution between 219 and 255 square meters per gram. With this series of catalysts, we were again running hydrotreating tests, and we observe for a pure molybdenum sulfide catalyst we see a very low HDS activity, but pretty good HDN and hydrogenation activities. The iridium catalysts, the pure iridium catalysts, show generally a very low activity in all experiments, for HDS, for HDN, and for hydrogenation. This is independent from which iridium source the catalysts were prepared. The bimetallic systems show a moderate activity in HDS. I should say this is referenced to a cobalt molybdenum catalyst, a standard cobalt molybdenum catalyst with about 13% of molybdenum and 2.6% of cobalt. The order of activity for the iridium molybdenum systems is this one here is best from acetyl-acetonate iridium. The second one is this one from iridium carbonyl, and the system with the lowest activity is this one from hexamine iridium trichloride. The same order of activity is observed for HDN, but here the activity is much higher than for the reference system. In the case of this iridium molybdenum catalyst from acetyl-acetonate iridium, the HDN activity is twice as high. You might remember that molybdenum, that the iridium content and the cobalt content on these catalysts is slightly below 3%, but since iridium is more than 3 times heavier in molecular weight than cobalt, the molar concentration of iridium is much lower. For hydrogenation, these molybdenum iridium catalysts could not compete with a cobalt molybdenum reference. So we see the selectivity of iridium molybdenum systems is rather different from the cobalt ones. It is more similar to a pure molybdenum catalyst, molybdenum sulfide catalyst. And this is of course an important point when we try to understand the structure of an iridium molybdenum system. In order to elucidate that structure, we have carried out EXAFs, and this is an in situ EXAFs where the catalysts are sulfided and with this gas mixture. So this is approximately the same process which is going on in a light treating reactor. We can see here 3 Fourier transforms of X-Ups curves. One is a reference, a molybdenum sulfide reference, and the 2 lines in red and blue are the iridium molybdenum systems. This first signal here, here are 3 lines superimposed on each other. This is the first coordination shell around molybdenum, the sulfur atoms. So we see all 3 samples are fully sulfided. The second signal here is showing the molybdenum-molybdenum interactions. Here we have again that the 2 lines for the iridium molybdenum system are superimposed on each other, so there is no difference from the molybdenum point of view for these 2 catalysts. There's just a difference for molybdenum disulfide, and this is that the degree of dispersion for the iridium molybdenum catalyst is much higher than for molybdenum sulfide. So the difference for in reactivity for these 2 cluster systems, these 2 catalyst systems, must be something different. And we also carried out X-Ups for the iridium edge. And here we found some interesting differences. The coordination, we found that the coordination for iridium from this iridium carbonyl system is much higher than for the second system originating from iridium agave. This can be explained by the bond energy model dominated by the promoter atom. This interpretation is, we got further evidence for this, for this observation by temperature programmed reduction of sulfided iridium molybdenum catalysts. We can see in the upper plot the concentration of consumed hydrogen versus the temperature, and in the lower plot the concentration of liberated hydrogen sulfide versus the temperature. We see in the upper plot that iridium is reduced, an iridium catalyst is reduced at the lowest temperature, and molybdenum catalyst is reduced at the highest temperature. The curve for an iridium molybdenum system is in between these, and this is a temperature difference of about 10 degrees. And this thick curve is not just the 2 thin lines superimposed. So we carried out similar investigations on cobalt molybdenum and nickel molybdenum systems, and found a similar decrease of temperature for this peak maximum. So there is a correlation between this decrease in temperature and the metal-sulfur bond energy. This is also the conclusion for the iridium molybdenum system. Iridium reduces the sulfur bond strength and creates more vacancies, more sulfur vacancies. So this is in our mind the reason for the enhanced activity in comparison to molybdenum sulfide. Finally, I would like to thank some people from Topsøe Group, Henrik Topsøe, and you Topsøe, and many other colleagues from other Topsøe. Thank you.
Thank you, Konrad. Any questions on this paper? Yes, in the back.
Very nice work. I have one question on your TPR phase.
species, yes.
And what happens to that when, obviously you don't see that when you incorporate molecules.
No,
Yeah,
but in this case you form a kind of iridium molybdenum sulfide phase.
right.
So this might be the reason that you do not observe here an additional peak.
Yes? Other question?
Yeah.
Konrad?
Do you have any information about the selectivities for the HDN on HDS reactions?
You mean
Are they different from the promoted to the molybdenum catalyst?
this is you mean here? This is the unpromoted molybdenum catalyst, and these are the with iridium.
Yeah.
So the selectivities are, at least for HDS and HDN, pretty much the same as for molybdenum. Hydrogenation, this is a lower factor, so you cannot increase the hydrogenation so much as for HDN and HDS.
I was asking about selectivity, for example, through hybridization or CS bond pathways, for example, in the HDS of DBT.
No, we don't have so many data for that.
Another question?
Yeah, I'm just wondering, since you put iridium into the catalyst, hydrogenation activity is decreased. So if you try this catalyst system for hot sulfur, like dimethyl or dimethyl substitute, DBT, will you be able to see the advantage of this addition of iridium to the system? Because for the hot sulfur, hydrogenation activity is very important.
Yes.
I'm just wondering, have you tried that?
No, we have not tried that. No. Just these identified fields in order to leave the system.
Yes? Another question?
My question is related to the previous one. If iridium is really making easier to form the vacancies, the sulfur vacancies, in this case, how come that the hydrogenation rate is not increased? Hydrogenating, you will need actually more vacancies than for doing HDS. So you seem to have about the same rates of HDS and hydrogenation for both systems.
Showing some new aspects
Whereas
which
for
we
the
don't have here.
only molybdenum catalyst, you increase, you have a ratio of about 7 times HDS with hydrogenation. In the other two cases, you have almost a similar. It doesn't seem to fit the idea. We're increasing the number of catalysts.
Comment or question?
Just a question.
Okay.
Have you tried the any relative HDN activity for with respect to nickel, moly, and alumina, and compare that with moly, iridium, and alumina?
Molybdenum, no, we have not compared.
Just wondering if it's a better catalyst for HDN compared to that nickel, moly, alumina.
Yes, yeah.
That would be an interesting comparison
Yes.
with the nickel.
Yes, because when you're comparing with cobalt moly on alumina with moly, iridium, and alumina for HDN, HDS I can understand, for HDN I think that's a better study to see this.
Any other questions?
I have a question related to the Cuban preparation. I didn't fully understand Cuban structure are soluble in water when you keep the water ligand. So I didn't understand why did you go to the organic ligand in order to have the preparation in organic solvent.
We did that in order to study the interaction, for example, with sulfur-containing molecules in organic media. So we could run NMR spectrum, for example.
Means recording
Sorry?
With sulfur ligand.
Yes, yes. Organic sulfur-containing molecules.
What are you looking for?
Well, we were trying to crystallize, to get crystal structures for these kind of catalysts. We also were trying to use these clusters as model compounds for X-up spectra.
May I ask another question?
Sure.
When you're doing the TPR for sulfided catalyst, so you first sulfided and then run the TPR, right? I was wondering if you tried, like when you sulfide the catalyst in a fixed bed or trickle bed reactor, have you tried taking the catalyst from different parts of the reactor and doing the TPR just to see the extent of sulfidation? Because your conclusion is it has been fully sulfided.
Yes.
I was wondering if it has anything to do with where you're taking the catalyst from the reactor for this.
No, this is in very small amounts. These model studies are made in just below 1 gram. Yeah.
Are there any more questions? Okay, thank you, Konrad. That was